Hello everyone. The purpose of these videos is to make sure that everyone is comfortable with the lab experiments on Ansys HFSS and there are no confusions while performing the experiment during the main exam, the main lab essays. So initially I'll just go through some of the main commands on Ansys HFSS which you need to be familiar with to perform all the five experiments. Then later on I'll just dictate a little flow of all the five experiments. The flow of all the five experiments is quite similar, just that the design and structure that we'll be making is different. So yeah, initially I'll go through the flow and then we can get started with experiments one by one. So I'll be performing or demonstrating all these experiments on ANSYS 2024 R2 student version. The version that is available over the lab computers is 2023 version. There are not many changes or there are not many, there's not much difference if you compare, but wherever there is difference, there will be a difference. I will try to highlight that and make sure there are no confusions. So this is how the window will look as you open Ansys. And then here you click on HFSS and you get this window. So basically you have a project manager tab over here, and here you have a tab where you can check the structures that you'll be making. So yeah, basically the basic commands are these. So you can see this coordinate axis over here. So you can just hover over this, and if you just press and hold, you can move and see the entire coordinate system. And if you just click on this little dot over here, you can get this top view, and which will be pointed towards plus Z axis. And if you say click over here, you'll get the side view and so on. So I'll just stick with this for a while and show you some other commands like pan. So this command pan will help you move around like this. If you just press and hold, you can just move around and check your structure. And there's also rotate command where you can just rotate and view your structure. And then there is fit all command. So if you press this, all of the structure that you have made will be visible completely. Like everything will be fit on the screen once you press this command fit all. And then yeah, in Project Manager, you can check out the HFSS design. So if you click on this plus mark, little plus mark over here, you can see all these things: analysis, optometrics, results, excitations. I'll be explaining as I go along what exactly these things mean. And then there's also these planes, lists, and coordinate systems. So this is the global coordinate system that you see XYZ. And yeah, there's some planes. And as we make the structure, you'll start seeing the rectangles, the boxes, and everything over here, which will be helpful for us to manipulate in terms of coordinates and get our desired structure. So these were some of the basics of this tool, Ansys HFSS tool. And coming to the flow of each experiment, uh, there are basically five experiments, and in three of them, you'll be doing stacked structures. So the first one is microstrip line, then there is hybrid ring coupler, and then there is patch optometrics. So all these three are stacked structures where you'll be stacking one layer on top of another and getting something. So that those are all three stacked structures, and the other two, which are rectangular waveguide and magic T, are like 3D structures. So these two are two different sets of experiments, and the basic flow that you'll be following for all of these, and mainly if I talk about the stacked structures, is to first build a ground plane, and on top of the ground plane, you build a substrate layer, and on top of the substrate layer comes the microstrip line or the feed line, which you say. So this is the stacking layering that I can say. And after this stacking, you'll be assigning port, and the port is to pump in power to that structure. So after that, you'll be creating a radiation box to that entire structure. The radiation box is to make sure that the measurements that you're doing, that is, the results that you're checking, are properly in line. Without the radiation box, you won't be seeing the right results. That, and before checking the results, you'll be adding something called as analysis. Analysis is basically like you're solving these electromagnetic equations for this specific structure, and those electromagnetic equations needs to be solved in a computational way, and for that you'll be interpolating the equations and doing all sorts of discretizations. So for that you will be giving some parameters, and based on that the analysis will be carried out. So this was the basic flow that I wanted to talk about. For all the experiments this will be the case. So coming to the very first experiment, microstrip line. Um, so talking about microstrip line, the point of performing the experiment is to check how good that microstrip line is transmitting the power that is pumped in. So a microstrip line has ports at two ends, and whatever power you pump in at one port should completely be transmitted at the other end. That is the point of a microstrip line. But here, since we are performing practical simulations, you'll see that not everything gets transmitted and there are some reflections. And the point is, at a particular frequency, you'll be designing this microstrip line. So the parameters of the microstrip line are directly dependent on the frequency. So you're choosing mostly here 2.4 gigahertz. So for 2.4 gigahertz, there'll be very specific parameters of the microstrip line, the substrate and the ground plane. You'll be choosing them accordingly. And then you'll be checking these S parameters and electric fields. So the S parameters will help you determine that how much power is being transmitted through the microstrip line and how much is getting reflected. Ideally, everything should get transmitted since it's a microstrip line. But yeah, you'll see that there will be some reflections, and unless the reflections are under a certain value, you'll see that it will not be a concern for us. So we'll just have to make sure that some of these parameters are in line with what we are doing. So let's get started. So for the microstrip line, I'll be drawing a ground plane first. As I mentioned, the very first process is to start with a ground plane. So before starting with the stack structure and the ground plane and everything, I just like to give some background on the geometry that goes behind all of this. So when you draw a rectangle, and yeah, here's my rectangle. So when I draw this rectangle and double click on this create rectangle, you can see that the position is quite random, which you don't know because you just hovered over a point and you drag and drop. So you don't know what the position is or x size is or y size is. So I really want a 20 cross 40 rectangle over here, 20 cross 40 rectangle. So I'll just change my x size to 20 and y size to 40. So that will create a 20 cross 40 rectangle. And the position is really unknown here. Unknown in the sense it's not very accurate for simulations, I would say. You can still do the structure here, you can still do the stacking at this position, and you can still get the results. But to make the job easier, what I can do is first I can align this thing at origin and see which point is moving exactly. So now you see that this point of the rectangle is oriented at the origin. So it is this point which is moving. And to make things even more simpler, I can just make the 0, 0, 0 come at the center of the rectangle. For to do that, I just have to move this point, this corner of the rectangle, minus x by 2, which is minus width by 2 and minus length by 2 in x and y directions. So let me just show that. So it goes like this. First, I'll move minus x by 2 along x direction, and you can see that now this point is at the center and the corner has moved by this much. And if there's a way I can orient this at the center of the rectangle, then I need to move along minus y in steps of y by 2. So I'll just select here and move minus 40 by 2. So now you can see that it's properly stacked, not stacked, but it's properly aligned such that the center of the rectangle is the coordinate system's origin. So now things become much easier and you can start simulating and start stacking structures on top of this. This way the geometry, you don't have to worry much about where the position is, where the point is and all that. It becomes much easier. So this is the way we do the geometry on your screen. And now I can just show you the 3D view of how this looks. I'll just hover on this and rotate a little bit. So you can see that this is the ground plane sitting on this coordinate system, and it's at the very bottom. And on top of this, there'll be substrate. Before assigning ground plane, substrate, and all these things, let's just complete the structure first. And to make things easier, you can always right click on this rectangle one and change the color so that things are easier to see. Like, and I can just apply and make sure that ground plane is in this color just to differentiate what is what. I just double clicked on this rectangle one and I saw this color. Just double click and usually this is in this color, the ground plane. So I'll just select this and press OK. You can see the color. So now I have my ground plane and on top of this will be the substrate. So for the substrate, I'll be selecting a box. Why box? Because the substrate has a certain thickness and that thickness is 1.6 mm over here in all the experiments that we'll be doing. So the substrate is basically a dielectric material and this dielectric material is stacked in between the ground plane and the microstrip line. So this the dielectric will have certain properties like dielectric constant and loss tangent, and these are key parameters for matching whatever characteristics we want for the microstrip line in terms of frequency and all these things. So here we will be using FR4 substrate of 1.6 mm thickness. So I'll be selecting this. And now that I've already assigned the coordinates for this, it's quite easier to draw a box. So I'll just hover over this point. This is the exact point that you see, and you can always zoom in as much as you want by just using the cursor. So you see, when I see this little black rectangle, it means that it's at the very exact point as the endpoint of this rectangle, this ground plane. So all these points are different, and this point is that endpoint. So I'll select this endpoint and go all the way till this endpoint. And since it's a box, I will have to select another point, which is up and down. So I will just move it somewhere here and press. So now you can see the 3D view of this. I have not exactly selected the Z height here. I just made a box of random height. We'll use fit all command. And you can see that this has a very random height. So what I'll do is I'll just go to this create box and you can see I've given it a very huge height. So it's causing some issues. So I'll just give this height 1.6 mm, which is what is required. And again, I'll make sure this is minus x by 2, minus y by 2, 0, 20, and 40. Now if I apply, now you can see that this is the ground plane and on top of this is my substrate. So this is the way it looks. Just to give you guys a feel of this. This is the ground plane and this is the substrate. And now again I can be back to my comfortable view, which is this. So on top of the substrate will be the microstrip line, which will be basically transmitting the electromagnetic energy or the power. So again, for microstrip line, it will be grounded. So grounded as in it will be perfect conductor. So I'll be using a rectangle. So I'll select on the draw rectangle and select any point over here. So if you guys have seen the uh, lab manual, the figures that I've demonstrated, the microstrip line goes something like this. So I'll select some random point here and then extend this like this and drop it over here. Now, this rectangle has come somewhere at the bottom. As you can see, it's here and I don't want this here. I want this on top of the substrate. So I'll use create rectangle, double click on this, and you can see that the position of this is -4 comma 20 comma 0, which I don't want. I want the x size, that is the width, to be 3 mm and the y size to be 40 mm, which will be covering the entire substrate or the ground plane. So I fix my x size and y size, and accordingly I can vary the position. So the position will be x size is -3 by 2 comma -40 by 2 comma 1.6. Why 1.6? Because this thickness is 1.6 and I want this microstrip line to be on top of this substrate. So 1.6. So now I'll apply and you can see the 3D view first. So there is ground plane, there is substrate, and then there is microstrip line. And if I just come back to my original view, you can see it's properly centered. And again, I can always change the color of this also to orange. So here is the microstrip line. And now you can see the final 3D view. This is how it looks. So this is my basic structure. So now what I'll be doing is assigning materials to everything. So as you can see, this is rectangle 1 is ground plane and this rectangle 2 is the transmission line. So I'll just select these two and right click on this and go to assign boundary and select on perfect E, which means perfect electric field or perfect conductor. So I'll just select this and it will ask for a name. This is fine. Then press OK. So now you have assigned these boundaries, that is perfect E boundaries, to both the strip line and the ground plane. And you can always see these boundaries over here at this column. This says boundaries. If you just hover on top of this plus and you can just see this is how the boundary perfect E looks like. Yeah. Then you need to assign FR4 substrate to this box. So initially you can see it's vacuum. So I'll just click on this box, right click, assign material, and here you'll get a list of all the materials. So I'll just search by name FR4. So you can see this is there, FR4 epoxy, flame retardant for epoxy. I'll just select this and press OK. So now this is also assigned. And now, since all the materials and boundaries are assigned, I'll draw a port. A port for this should be on both sides, like at the transmitting end and at the receiving end. So as I said initially, you can zoom as much as you want. You can zoom in, zoom out as much as you want. And I suggest that for drawing a port, you zoom in as much as possible because you can always assign coordinates for the port and make it right. But then if you just do it in a visual way, it becomes a lot easier so that you don't have to assign coordinates and everything. It becomes a lot easier. So now you can see that I need to draw port over here at this face of the rectangle. And at this face of the rectangle, the plane is different. So all this while I've been drawing these structures on XY plane. And you can see the grid lines over here. So these are the grid lines for the XY plane, all these grid lines. But now I want a port on this face. So I need to change my plane to XZ. And now you can see that the XZ plane is over here, where the plane of this rectangle is. So this rectangle face is parallel to this coordinate plane, XZ plane. So now I can draw my port on this face of the rectangle. So I can zoom in as much as I want and then click on rectangle and then make sure that it's at this very point. And you see the small black rectangle. Click on that and then keep moving and zoom in as much as you want. And now you can see this dotted line that comes up. So make sure that it's aligned with that uh, the other end of the transmission line and then just drop it this way. So your one port is done. Now that you have assigned it properly, you don't have to go to these coordinates and do all this setting because it's much easier to do it this way. Again, it's not a hard math to figure out the coordinates. It's just that you'll be drawing it in the uh, axis XZ plane. So the axis becomes Y and the width is 3 mm and it's at a Z size of minus 1.6 and these are the coordinates for the same. So it's not that hard to determine these positions, but it's much easier to do it this way. Just be careful that all these parameters match and you're careful and you're zooming in as much as you want to make sure that it's drawn properly. So again, I'll just rotate it this way and draw a port at this end also. So again, the plane is XZ, click on draw rectangle, and this little rectangle that comes up, and then select, zoom in as much as you want, and yeah, now you can see it's properly aligned. Then drop it here. So your port is also assigned. Port is not assigned to be precise. You have drawn a port, and I need to assign excitation for these ports now. So to assign excitation, I'll just click on this port and right click and go to assign excitation, port, and model lump port. So the impedance of this port will be 50 ohms. That's a standard for minimal reflections. And I'll click on next. And then here you can see something called as integration line, which has been defaultly selected as none. So I'll just click on this and say new line. Then you'll get this dot where you can draw the new line. And when you're drawing it, again, make sure that you zoom as much as you want. And then when you're at the very center of this port, you'll see this small little triangle, and that is where you need to start drawing your port. So I'll just select this point where that small triangle comes up, and I'll drag it above. And again, you'll see the small rectangle. That is where you drop it, and then click next. Then finish. So you've assigned excitation to your first port now. Then I'll do the same for another port, which is over here. Zoom in and right click, assign excitation, port, model lump port, and this will be your second port. The name for the first port was 1, and this is your second port. So next, and then new line. So we are done with the stack structure now. I've assigned excitation, I've assigned boundaries, and I've assigned the material. So this was about the structure, and I'll come back to my XY plane. And one small thing to note is that you won't see these planes directly on Ansys 2023 version. So you'll have to go to something called as visibility. You'll see that column in draw. You'll see something called as visibility. And if you click that visibility, then you'll see this grids and axis. So that's one change from 2024 to 2023, which you need to note down. So this is the structure done. And now I need to create a radiation box. As I told, we have designed this for 2.4 gigahertz. So I need a radiation box which supports radiation characteristics testing for 2.4 gigahertz. And there's a very complex method that's given in manual to create a rectangle, to create a box and assign it radiation boundary and all that. I'll just tell you a very simple step to create the radiation box. You just right click anywhere and there is something called as create open region that you see. So just select that and select this operating frequency to be 2.4, give the value and enter. So it will automatically create a radiation box for you. and you can see that this radiation box looks something like this, modeled with thick red lines. And you can always hide this radiation box because it's not very convenient to use keep looking at this radiation box when you really have to play around with the structure. So I'll just select this radiation box and hide this, and you can see this is the command to hide selected objects in active view. So now that radiation box is there, but it's just hidden. And when you click this and select the radiating surface back, you can see the radiation box again. So I'll just hide it for now. This is created, and then as I said, the next step is to analyze this. So I need to add an analysis setup. So I'll just right click on analysis and go to add solution step, then advanced. And here you can see that it's asking for a frequency, which is 2.4 gigahertz. And here you can see something called as maximum number of passes. Just leave it at that. These are parameters that uh, are not at our interest right now. Passes means that the simulation will be run that many times to make sure the accuracy. So yeah, we'll leave it at that and select this frequency to be 2.4 and press OK. And here you can see that it's named as sweep, and sweep type is interpolating. Interpolating means that from 1.2 gigahertz to 3.6 gigahertz at 401 points, this solution step will be solved. That is, say 1. Whatever this 401 points are, 1.21, 1.22, something like that. So these many discretized points will be there for the electromagnetic solver, and it will start solving. So make sure it's 2.4 lies somewhere in between, and 1.23.6 is a good number, and 401 points are pretty much sufficient for us to analyze. So I'll just press OK now, and now my analysis is also added. After that, I'll be validating the structure and then simulating it. So from draw, I'll just move to simulation. And here you can see this command called as validate. So now if I press that validate, if you've done everything right, you'll get this 6 green ticks. And this means that you have properly designed your structure. Um, Boundaries and excitations are assigned, and then mesh operations, 3D model, since it's 3D model, then there are some settings, radiation box, analysis setup, everything is done. So it's validated now, it's good to go for a run. And I can just close this. And here you can see this project one, right? I can just rename my structure, whatever I've done. So I'll just right click on this and say rename, and I'll rename this as microstrip line. So this is my project, and this is HFSS design. I can just save it. So yeah, save it, and then press on analyze all. So this will start the simulation. So here you can see this button called as show progress. So here you can see the simulation running. So let's just wait for the simulation to complete. It won't take much time. Yep. So the simulation is complete now. I can go and check the results. So here you can see this column called as results. So if I just right click on results, I can plot whatever the results that have been simulated. So now I'll go to create model solution data report, and then over here rectangular plot. So here I'm going to select S parameter because that is what I'm most interested in. S parameters will tell you the reflections and the transmissions that have happened over the microstrip line. So here you can see S11, S21, S12, and S22. So I'll just press Control and select all of this and make sure that it's in dB. Now click New Report. So you will get something like this. So this graph depicts S11, and this graph depicts S22. And you can see that S12 and S21 are overlapping, which means that whatever you send at port 1, the power that's being pumped at port 1 to the port 2, the transmission coefficient, basically this S21 and S12 are transmission coefficients, they should remain the same. And you can see that these two graphs overlap. And there's slight deviation from S11 to S22. So to check exactly what this graph means, I'm just gonna add some markers. So I'll just right click and say marker, add X marker. So this brings in a marker, and if I just drag it to the peak point, I can see these values. It is 2.5 gigahertz and minus 40.95, minus 40.96, and there's minus 0.32 and minus 0.32. So you can see that at this specific frequency, 2.5 gigahertz, the S11 value or the reflection coefficient is minus 40 dB, which means that most of your power, that is around 99% of your power, is getting transmitted and there are minimal reflections. And if you look at this, which is S12, the transmission coefficient between port 1 and 2 is close to zero. This means that the transmission is happening across the two ports, and S11 means you're measuring reflections at the port 1. So here the reflection should be very minimal, and here everything is that is everything should be transmitted, and S12 means between the two ports everything should get transmitted. That is the transmission coefficient and the reflection coefficient. The standard value is something below minus 10 dB is very good for minimal reflections, and here we're getting minus 40 dB. That means it's pretty good, and this is also close to zero. So those were some parameters. And one more thing that's important is to plot the electric field patterns on top of the microstrip line, which is usually asked. So I'll just, from results, I can move back to my structure by clicking on this HFS design, double clicking on that. So here, plotting electric fields and animating it is quite simple. So I can just select this microstrip line, then right click, and then go to plot fields, E, and Mac E, and it will show you this thing. You can just press press done. So here you can see the electric field has been plotted, and this is like for a particular face. And if you want to animate this, you can just go to this field overlays and click on this plus, and then right click a little, press animate, and then press OK. And again press animate, and you can increase the speed here. So you can see that the transmission of electromagnetic energy is happening. Everything is getting transmitted and there are minimal reflections. This is what we wanted to see. This is what we conclude from this video of experiment 6A microstrip line. Thank you.
So moving on with the second experiment, which is the hybrid ring coupler. So the steps that will be followed here will be very very similar to what we did in the microstrip line. It's very intuitive, and it's just gonna be a little different from microstrip line, where you saw in microstrip line that we were transmitting from one port and receiving at the other port. Over here it's different. We'll have four ports here. The basic idea behind a hybrid ring coupler is that out of the four ports, when you pump in power through one of the ports, the power is divided amongst P2 and P4, which is port 2 and port 4, where port 3 is isolated. So it's called as 3 dB isolator, or 3 dB coupler also. It's like basically like magic T. If you remember how magic T works, it's very similar to magic T, but magic T is like more like a 3D structure, where you have one arm extending over the z axis as well, but here it's completely in the plane and it's a stacked structure. So let's begin. In the lab manual, you'll find that very first they start with uh, two circles and subtracting them. But you can do that, and the other procedure that we've been following is starting with the ground plane. So you could also do that, so I'd prefer that, and just draw the ground plane first. And here in hybrid ring coupler, it's hexagon, so I'll start by drawing a regular polygon. So I'll just select this option, and from the center I'll just draw this, and it will ask for number of segments, and since it's a hexagon I'll be entering 6. And again you can see that basically I have drawn a very random hexagon here without assigning any length or position for it, and I want to design this for 2.4 gigahertz. So there are very specific parameters for 2.4 gigahertz which I know by calculations, and it's given in the manual after all the calculations. So basically, the radius here would be 30 cos 30 mm upon cos 30 degrees. So that is what the radius of this hexagon is. That is starting from here to this endpoint. That length is what I know for 2.4 gigahertz C band hybrid ring coupler. So since I know that, I'm just gonna double click on this create rectangle, and see, as you can see, the center position is 000. So I started drawing the hexagon from the center. So this center position is 000, and the start position represents wherever I dropped this endpoint. Now I know that this endpoint was dropped at the radius, and that radius I know is 30 mm upon cos of 30 degrees. And since it's taking default values in radians, I'll just multiply with pi by 180, and the y and z coordinates will be 0 for this, because I want it to be planar and I don't want anything to extend over the y axis or z axis. So this is a planar ground sheet, and you can see that the number of segments are 6, and I'll just apply and then use this fit all command. So now you can check out the 3D view. You can see a proper hexagon. So this is a 2D figure, and on this we'll be stacking the substrate. So yeah, moving on to design the substrate. Substrate is of thickness 1.6 mm, and the material is FR4, as we all know from before. So instead of the 2D one, I can just select this one here, which is a raw regular polyhedron instead of a polygon. So I'll just select this, and again start with the center position 000, and just drop it somewhere here approximately. And again, as I was saying, here you'll be moving along x and y also. So you can see I'll just select some random height. Number of segments is 6. I'll just press OK, and the coordinates for this will be same for the hexagon. So I can just double click on this create polyhedron. Center position is 000 as usual, and this will become 30 mm upon cos 30 into pi by 180. Make sure you write mm here, because otherwise by default it may take some other value, some other unit. So make sure you write 30 mm upon cos 30 degrees. And I also need to extend this to 1.6 mm, because the height of the substrate is 1.6. So I'm gonna give it a thickness of 1.6 mm, and that will be depicted here. Like this is 0 to x1, 0 to 0, y nothing has moved, and 0 to 1.6 mm means that from starting from 0 it's extending up to 1.6 mm is what this means. And here yeah, so here is the height, which is 1.6 mm. And yeah, I'm sorry, this will be 0 because it's asking for the height here is 1.6 mm. So I just entered it there, and I'll apply this. So now you can check the 3D view of this. So on top of this ground plane is my substrate, and you can view it properly. And again, I'll change the color here by double clicking on polygon 1 and going to color and just change this. So now I can see the ground plane properly. And after this comes the strip line and the feed lines. So for that, it's been the radius of two circles have been given, which are specifically for C band 2.4 gigahertz. So it's better to remember those precise values of the two circles that we'll be subtracting. So I'll select on draw circle and start from the center and drop it here. And here I can allot the coordinates. It's pretty simple for circle, it just asks you for the radius. So I'll just drop in 17.52 mm, and the center position is 001.6 because the circle is being drawn on top of the substrate, and substrate has a thickness of 1.6 mm. So it's 001.6, and the number of segments are 0 for a circle because it's an infinite sided polygon. Yeah, and I have a 17.52 mm circle, and similarly I'm going to draw a 15.9 mm circle as prescribed by the manual. 15.9, it's taking in mm. Now what I'll do is I'll have to subtract the two circles because this part is what I don't want, the highlighted part. So to remove that, I'm just gonna have to subtract that smaller part from the bigger circle. So I'll select the bigger circle first, then the smaller circle by using a control command, and then you can see this command called as subtract over here, and here it's clearly visible in 2024 version, but on 2023 version you will see something called as operations, and if you click that operations you will get this option to subtract, and I'll click this subtract and just select OK, and now I have this ring. Yep. So after the ring is a little bit of a tricky part, I would say, is to draw those feed lines. So it's very intuitive, to be honest, because the width of these feed lines is 3 mm. We know that, and the size, that is the length of this, will be precisely this much, starting from here and ends here. So this length is approximately 14 mm, which is known to us. So I can directly just start drawing a rectangle and just drop it somewhere here. And it's not visible here because now you can see that it's gone below, and now we know what to do exactly to get it where we want to. So as I said, the X size is 3 mm, and you can see the length I fixed it, like I drew it from this point to this point, so it automatically took 14 mm. So I'll just leave it at that, and then say this is minus 1.5 because I explained the geometry earlier. Like this thickness is 3 mm, and the end point that it goes to is here, and that end point, if you calculate the position with respect to origin, it's minus x by 2, and that's minus 1.5, and the position in z will be 1.6 mm because it's on top of the substrate. Now I'll just press OK, and here you see this. Okay, so I'll, as usual, change the colors for convenience. The strip lines I'll be giving this orange color, even the ground plane, and even this. Yep. So after this I have to duplicate this 4 times by rotating it by 30 degrees. It's quite simple. If I just select this and go for this option, which is duplicate around axis, yeah, this one, duplicate around axis. If I just click that, and now you can see a copy of this one coming over here. So what I'll do is I'll just give the angle as 60 degree and the total number of objects as 4. So now you can see 4 things being placed over here. So it's still not placed because I've not applied the command yet, and you can see how it looks. So once you can see that it's properly placed, make sure that it's 60 degrees and the number of objects are 4, because counting this one, the duplicates are 4 in number. So I'll just press OK, and now you have all the duplicates. So now what I'm going to do is I will have to unite all of this because this is the same thing. So I will just be selecting all of these things and clicking on unite. This command will be visible in operations in 2023 version. So I'll just press unite and everything is united. So now, as usual, the next step is to draw ports. And ports, as I said, rather than the geometry, the more easier way to do it is just visual way. Just a visual way is very efficient. So I'll just change the axis to XZ axis now. As mentioned before in Microstrip line, I have explained it properly why this XZ needs to be selected, and I'll start drawing a rectangle. Starting from this point, you see a small rectangle, and properly align it over here. Zoom in as much as you want, and then now you can see the port is properly aligned. So just drop it here. Now again you can do the same thing for port also. Just use this command called duplicate around axis, and yeah, so you can see the number of objects. It is just taking the previous values, 4 in number and by 60 degrees, so it's properly already assigned. So 60 degrees angle and number of objects are 4, and I'll just press OK. So I have 4 ports also now. Yep, so the next step is to assign materials to all of this, and I'm gonna be back to my XY axis just for my convenience, and I will select this circle and this polygon, which is the ground plane, and these are all ports, so I'll worry about it later. And I'll just go here, assign boundary, perfect E. Okay, done. And this is FR4 as previously mentioned. FR4, I'm just gonna search for it, press OK. So that's also assigned now. So now I just have to assign all the ports here. So I'm just gonna select each port and go to assign excitation, port, model lumped port, and next, and new line. Just gonna zoom in as much as I want, wait for that small triangle to appear, then follow the same steps. Just rotate it by a little bit. Same process will be followed. Yeah. So this is all done. Now to verify that you have added the ports properly, there's a way to do it. So you can just click on this plus and go to excitations. So it's very confusing sometimes to check whether you added ports everywhere properly, because sometimes what you can do is, while rotating, you can add same ports twice on this, and here somewhere the port might get missed out. So I'll just verify if I've done everything properly. So I just went here into HFSS design, click that little plus, went into excitations. So this is port 1, which is over here. You can see that properly, like this is the first port, then the port 2 is over here, port 3 is over here, and port 4 is over here. So I've done everything properly, and yeah, the structure is basically ready now. It was quite simple as we navigated through. So now the next step is to add the radiation box, as we mentioned in the flow. So you just right click and select on create open region, operating frequency is 2.4, and you have a radiation box. And for convenience, I always like to hide the radiation box by selecting on it and selecting the hide command. Yep, so the structure is ready now. So now the next step is to add the analysis. So I'll just go to analysis, add solution step, go to advanced, and the frequency is 2.4 gigahertz. I'll press OK. Then yeah, this you can leave it at this because you want to see 2.4 gigahertz, and it's almost at the center, and the number of points are 401, which is quite sufficient. I've explained all of this before in the strip line, so I'll not go in detail. and then select this. So the structure is ready now. I just have to simulate and analyze the structure. So now you can see I will just go to simulation and validate. So everything is proper. Now I'll rename the project to hybrid ring. So now I can analyze. Again, I can check the progress over here. It will take like 2 to 3 minutes, I think. Yep, so the simulation is complete. So now as usual I'll be checking the S parameters. So for that I'll click on results, right click, and go to create model solution data report, rectangular plot. So here I'll be selecting S parameters, and you can see uh, so basically when I am checking at port 1, I will have to check S21, 31 and 41, because as I mentioned before, when I'm pumping power through port 1, which is this, port 4 will be isolated, and the power divides between port 2 and port 3, which are these two. So I'll just check these as parameters, and you can see. So to analyze this, I'll be adding marker. To do that, I'll right click and go to add marker, add X marker, and I'll just slide this over here. So you can see this minus 3 dB coupling happening, and the port reflections that you're seeing here, which is S11 here, is well below minus 20 dB, and this one is S31, is also below minus 20 dB, and you can see the power division which is happening over here, which is the minus 3 dB. It's not precisely that because of the parameters that I've taken here. It's probably not very close to that frequency range. So you can see it's not even it's 2.36 something. It's not 2.4 to be precise. So we can perform the optimizations later to bring this properly in line with what we want. So these are okay for good like studies, current studies. This is fine. And you can also similarly plot other things, like you can go similarly to rectangular plot and then check S parameters, and you can actually check all the port reflections, which is S22, 32, 42. So 22 is the reflection, 44 is the reflection coefficient, and 33 is another reflection coefficient, 11 is another. I can check 21, 31. Yeah. So now I can see and analyze more. So you can just analyze this based on uh, what is being asked in the question or during the viva or whatever. So you can just plot and show the hybrid ring working, how it is happening. And the other step, of course, is to plot the electric field. I'll just be back to my design and then select this, right click and go to plot fields, E, and then mag E. Then press OK over here. So this is the electric field that you can see it here. So I'll just animate it, and to animate it you just go over here, click on this little plus, and then press on animate, press OK, then again animate. I can just increase the speed so you can see the isolation that is there. this one is isolated, and the power is being divided between these two ports. This is what you need to show, and based on this field simulation you can plot what you want, like check which port this is, and you can plot S11, S12, S13 and S14. So you can analyze much better by looking at this electric field simulations. So here you can see this is getting isolated. So that was about this experiment. I hope it was all clear. So it's a simple experiment. You just need to practice it once or twice, and you'll be very comfortable with the simulations. Thank you.